Hello guys, welcome back to class. In this session, we'll study about red-black trees. So in the previous session, we have seen AVL trees. AVL trees are self-balanced BSTs, self-balanced binary search trees. And we have done that. So we'll start with red-black trees. Red-black trees. Red-black trees also, these also self-balanced BST. So there are two things. Red-black tree is a binary search tree. Red-black tree is a binary search tree, and it is also a self-balanced. The only difference when you compare with AVL trees is how you are balancing AVL trees is different, and how you are balancing red-black trees is different. That we can compare once the red-black trees are completed. So red-black trees are not so strict. These are not very strict. Not very strict like AVL trees. So why these are not so strict, you understand on the way. So here everything is based on, we'll just play with red node and black node. So your BST contains red node and black node, RED red. BST can have multiple nodes. It contains, if you see a small diagram, I'll take black node as a black only. This is, say, 10 I have, and say 5 and 15. So here in this example, we have 3 nodes available. Root is a black, and 2 childs, 5 and 15, are the red nodes. This is a valid red-black tree. So when you represent a node, what is the information you are storing as? Generally, in the trees, node means you are storing first data or the key. Data or key you are storing. Then you are storing node left pointer. Then you are storing node right pointer. These 3 you are storing commonly. In addition to this, we're going to store extra 2 more things. Int color, 1 more field required to represent color. So here, the 10, you are storing the data as a 10 here, and its left reference 5 reference and right reference 15 reference, and the 10 is a black node, right? So black node means you're going to store some integer value. 0 means black. You can some representation. Say 1 is red. Either 0 or 1 to represent either black or red. Spelling I am writing always wrong. It is RED red. Okay. So in addition to the node value, that is a key, left pointer, right pointer, you are storing the color, whether that represents whether node is red node or a black node. In addition to this, one more important field also required for us, node parent. For every node, we need to have a parent address, parent reference also. So why parent reference, we'll understand on the way, but you understand the why color variable. Color variable is to represent whether the node is a red node or black node. And what every node's parent also will store. For example, when you're storing the 5, when you're storing this 5, so for the 5, key is 5. For 5, left is null currently, right also null, and color is color, because it is red, color value keep as a 1, and parent is 10th node, node 10. Node 10 is the parent. Why the parent required, we'll understand that. So, okay. So as of now, small changes in the node structure is you are adding 2 fields. Color to store the color of the node, either it is red or black, and also parent reference we are going to store. So remaining, it is a BST. So BST rules means for every node, left should be the smaller, right should be the greater. That BST rule is common because red black tree is a BST, and self-balancing we have to learn. We will learn that. Now, in this diagram, I given one example. This is a valid red black tree. That is a valid red black tree. And I'll take one more example. Say, I'm taking this as 10, and then 5, 15, and 20. This example, this is not a valid red black tree. This is not a valid red black tree. And 10, black color only I am using. 5 and 15. This also not a valid. This is not valid. This is not valid, but this is a valid. So how can I say a tree is a BST is valid red black tree or not? There are set of rules defined here. In the case of AVL tree, how you are identifying whether tree is AVL tree or not? In the case of AVL tree, how you are checking whether it is AVL tree or not? In the case of AVL tree, how you are checking whether it is AVL tree or not? In the case of AVL tree, how you are checking whether a tree is AVL tree or not? You are finding the height of, it is a simple, right? It is very simple to check whether tree is AVL tree or not. Find the balance factor. If the balance factor is either -1 or a 0 or 1, then it is valid. If balance factor is greater than 1, then you can say immediately it is not a valid AVL tree, and you can go for balancing it by doing the appropriate rotations. But here it is not so simple to check like AVL tree. There are set of rules to follow. Whenever you take the, so I'll just copy the rules first. You need to by heart. I think these rules you have to remember. I think then only you can identify. So I just have set of rules here. What are the red black tree properties? Are the rules? You say red black tree properties. The rule number 1 or property number 1. Every node is either red or black. Simple. Every node is either red or black. Next, root is always black. Root is always black. So if you go to the previous diagram, I have 3 examples here. This is example 1, example 2, and example 3. So you tell me here which rule we are violating. Why 2 is invalid? Why 2 is invalid, guys? Because root is red. What is a point when it is valid red black tree? Root always a black. Root always a black. So here root is red. That's what it is invalid. Okay. Come back. Next, every leaf node is say instead of nil, use as null. Leaf node or the null node. Here the in representation you have to do like this. Say first I'll go for black. I have 25 here, and then red, say 10 and 30. Then 10 childs are null, right? But you have to represent here as this is null node and this is null node. All the null nodes are black. This is null and this is null. You have to represent a null nodes. Means null is there. For your understanding purpose, I am representing null node. Because of this representation, what happens is, so what are the leaf nodes? We cannot say 10 is the leaf node now. We cannot say 10 is the leaf node. We cannot say 30 is the leaf node. If you are not writing the null representation here, what happens? For example, 25 is the root and it has two childs 10 and 30, which are the red. If I take this case, what happens? What are the child leaf nodes here? Tell me. In this is the first diagram, this second diagram. In the second diagram, what are the leaf nodes, guys? Second diagram, what are the leaf nodes? Second diagram, what are the leaf nodes? 10 and 30. But you should not take leaf nodes as red. Third point says your leaf node, every leaf node should be black. But my data node, 10 data node, 30 data node are leaf nodes, but those are red, which is against the rule. For that purpose, 10 has a two nulls. Anyway, 10 left is null, 10 right is null. 30 has a two references. 30 right is null and left is null. These nulls you represent as a null node, as shown in the diagram 2. Like this, you represent a null nodes here. Now, what are the leaves? Tell me. What are the leaf nodes in the diagram 1? In the diagram 1, leaf nodes are null nodes. Null nodes are the leaf nodes, and null nodes always the black. Null nodes always the black. So we have seen 2 points here. 3 points. Point number 1, every node is either red or black, okay, and root node is always black, okay. Point number 3, every leaf node or a null node is black. Here leaf nodes are the null nodes, or the null nodes are the leaf nodes. Those must be black. And go to point number 4. If the node is red, very important. If the node is red, then that node's adjacent nodes are black. Adjacent nodes are black. Rule number 4. If the node is red, adjacent nodes. What are the adjacent nodes? Parent and child. The nodes parent and child are black. Means, can I have a red child, red parent? As per rule number 4, can I have a red child and red parent? Tell me, guys. No. As per this, no red child and red parent. No red child and red parent. No red child and adjacent. If node is red, its parent must be black and child must be black. If a node is red, its parent must be black and child must be black. Must be black. So you cannot have red child, red parent, or the red parent, red child. So now go to our previous example. You take the example 3, guys, here. Example 3. As per example 3, why this is invalid? Tell me. Example 3, why this is invalid? Example 3, why this is invalid? Third, not second, Abdul. Second is invalid because the root is red. Second is invalid because root is red. Why third is invalid, I am asked. So 20 is a red. So 20 is a red means this parent you check. Parent is 15, also red. So red parent, red child, not allowed. Red parent, red child, not allowed. Red parent, red child, not allowed. That's what we are violating the rule number 4. Next, rule number 5. Every path from the node to its descendant null nodes, make it as null nodes, descendant null nodes contains same number of black nodes. Same number of black nodes. For example, you take this here, example 1. This example 1 you take. So every path from a node to its descendant null nodes start from this 25. From this to null node in this path, it contains the same number of black nodes. In this path, you see 1 black, 2 blacks. Okay. And from this path, you see 1 black, 2 black. Okay. From this path, you see 1 black, 2 black. Okay. From this path, you see 1 black, 2 black. Okay. From the any node you take, or you start from this only. Any node you take, I am starting from this. From this to null, 1 black only. From this null, 1 black only. From this you start. From this to null, 1 black only. In this path, one black. Any path, every path from the node to its descendant null nodes, any path, the same number of black nodes should be available. Same number of black nodes should be available. I'll take one example to make it invalid to show you. My root is a black, say 50, and here I have a 20, and I have here 15, 20, not 20, I'm not following BST. I'd follow BST rules, right? Very important. 50, and here I'll take 60. Okay. And I'd use the color. Here is the 40, and here is, say, 25 and 30, 25 and 30. So as of now, you see whether it is, as of now, you see guys, whether it is a valid red black tree or not. Check every rule. Check every rule. First, rule number 1. Rule number 1. Check, tell me guys, your knowledge, you have 5 points. You have to by heart these points. When you are solving the problem, these 5 rules should be in your mind. Then only you can understand the flow. Otherwise, every node is either red or black. Yes, I have 4 black nodes, 1 red node. Okay, either red or black, fine. Root is always black. Root is black only, fine. And leaf node, every leaf null node is black. I didn't represent, but if I represent that, say here I have a null node. Here I have a null node. Here I have a. It doesn't make any difference actually in the diagram. Initially, for your understanding, I am telling. Yeah, all nulls are black. If the node is red, its adjacent parent and childs only have single red node. Single red node. So 40, its parent you see, 50 is the black. Its childs are 2, 25, 30 black. So 4 also okay. Every path from the node, start from 50, count the black nodes in this path. 1 black, 2 blacks, 1, 2, 3, fine. In this path, 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 1, 2, 3, fine. I think this is a valid red black tree. This is a valid red black tree. Clear, guys? This is a valid red black tree. Rules are clear. Every node is either red or black. Root always the black. Every leaf node or the null node is black. And if the node is red, then all of its adjacent nodes, that is parents and children, should be black. Means no red parent, red child. Next, path from the node to descendant null nodes should have same number of black nodes. Whenever these 5 properties are followed, then you can say the tree is red black tree. Is this clear? Any doubts on this? Point number 5, explain once again. Oh, come here. You take in this valid are there. Okay, I'll take another diagram here. See, I have 50. So I'm taking 25 here and 75 here. Is this valid, guys? Check a look. Is this valid? Yes, it is valid. Right? Now I'll take here 10 and here 20. Now check, is this valid? This is not valid. Why this is not valid? What is our first rule to go? I'm writing the rules here. Rule number 1. Rule number 1. Root must be black. I'm following. Yeah, my root is black. Second, every node is either red or black. Yes, I have red and black nodes only in my tree. And rule number 3, guys, rule number 3, null nodes or leaf nodes are black. Yes, currently I didn't represent that. If I write also, I'll write in black only. So this I am not showing in the diagram. Rule number 4, no red parent and red child relationship. Parent child should not be red. Rule number 5, node to null node, node to null node, path, black nodes, number must be same. Number must be same. I think we are violating the rule number 5 here. Rule number 5. Pankaj, you are right. What's the rule number 5? If you go to this path, guys, in this path, 50, 10, 2 black nodes. In this path, 2 black nodes. But in this path, I have a single black node. So single black node means not okay. So this is not a red black tree. Means you are violating the property of red black tree. Then what I have to do, guys? Then what I have to do? Tell me what I have to do. When you violate any of these rules, when you violate any of these rules, then you have to balance this. Am I right? You have to balance this. Not only rotation, Pankaj. Rotation is not only the solution here. There are other ways also. So we have to balance it. How to balance it, we'll check later. You have to balance this. This is not a red black tree. You have to make it valid red black tree. You have to balance the red black tree. So how to do that, we'll see next. Suppose if I keep here as, suppose I'm inserting 80 here. Is this okay now? Is this okay now, guys? Now see, I think we are following all the rules. We are following all the rules, everything followed. Same black, black 2, 1, 2, and 1. Now, if I keep here as 70, now also valid. Now also valid. Okay, fine. So I hope you understand the rules. Now, you say red black tree properties means whenever red black tree is following these 5 points, whenever a binary search tree is following this, then you call it as red black tree. Fine. When you are generating red black tree, you have to cross check these points always. There are 6 points. These are the very, very important. Okay. Whenever you generate, you have to follow this. Go through these ones. Root is always a black node. So what I'll do, I'll try to take these points to my this. If you know these 6 points thoroughly, I think you are super good in okay. Come back. Yes. Are you able to see this font, guys? I don't know how to increase this font. I'm trying this. Yes, I think option is there. Let me try that. Yes, there is a chance to do that. Okay. Yes. So now, whenever you are generating, now you are writing a piece of code for generating the red black tree. So whenever you're generating red black tree, how you'll generate? You start keep on inserting, right? Whenever you insert the nodes into the red black tree, whenever this the corresponding rule is violated, you have to do the rearrangement, the rebalancing, right? So what are the rules we have to cross check and how to rebalance it or how to balance the red black tree? First, always you rule number 1 you see. Rule number 1 is you see the root always the black. So whether root is coming as black or not. Suppose I'm inserting my first element. For example, I'm inserting 50 guys. So means whenever you're inserting first node, keep that as black. Root is always black. Yes, rule number 1. Next, second point. Go to second point, guys. Second point is all the new nodes are the red color. First root node you insert as a black. Means how whenever you are inserting or adding nodes or inserting nodes, you check if root is null. If root is null means it is empty. As of now, there is no nodes in the BST. Because of no nodes, root is null. Root is null. You create a black node and make it. So my root is 50. Next, I am inserting another node. My next onwards, other than root, every node you insert, first insert as a red only. First insert as a red only. Say I am inserting 60 guys. Okay. Red only. Insert as red only. I am inserting 35. Insert as a red only. As of now, any problem? As of now, any problem, guys? As of now, any problem? I red inserted. You check the rules also. We have 5 rules. You should have those rules in a mind. As of now, no problem. So I inserted. Next, I am inserting suppose 75. what I have to insert 75, red node or black node? When I'm inserting a new node, what I have to do? You have to insert as a new node. And you read the third point also. Third, if the parent is black, nothing to do. If the parent is black, nothing to do. And again, I'll redo this. I inserted a root which is 50, always the black, done. I'm inserting 75, guys. What should I insert? Red. I'd insert a new node as a red. And if the parent is black, cool. Parent is black, 75's parent is black, so no problem. Next, again I'm inserting 35, for example. I'd insert as a red only. Yes, inserting as a red only. What is the parent of that? Black, so nothing to do. Cool. As of now, cool. Next, I am inserting 90. I am inserting 90. Where I have to insert 90? So my root is 50, 90 means greater, come to the right side. Again 75 is there, again come to the right side. So right of 75, right? So 90 I have to insert as red or black? 90, what I have to insert? Red or black, guys? It should be red, very good. 90 should be black, it is right of right. Now do you have any objection? Any objection, guys? Yes, you should have objection because red parent, red child not acceptable, red parent, red child not acceptable. Now see the fourth point in the rule. If the parent is red, because always you are inserting red, always you are inserting red. When you are inserting red, if the parent is red, then it is not acceptable. That's what, when a parent is red, check the color of the parent sibling. Check the color of parent sibling. So what I am inserting here, tell me? I am inserting 90. I am inserting 90. So current node I am inserting. You will learn this terminology. I'll explore it. What is the current node, guys? I am calling current node X. What is X? When I use a term X, it is always a current node. What is the current node? 90 you are inserting. What is the parent? What is the parent of this? Okay, parent is 75. What is the grandparent? Grandparent. 50. Very good. Now, what is the parent sibling? Parent is 75. Parent sibling. Wonderful. This is, so I am calling this for easiness. For easiness, I read this term somewhere in algorithm. Parent sibling, we can call it easiness as a uncle. So who is the uncle now? 35, right? So what is the uncle here? Uncle is parent sibling, we are calling as uncle. 35 is the uncle. So my current node I am inserting is 90. My current node I am inserting is 90. Its parent is 75. Parent sibling, that is uncle, is 35. Grandparent is 50. Now check the parent sibling color. Whenever parent is red, what you have to check? Check the uncle color, right? Parent sibling. Yes, uncle color is 30. That is important. Here is not parent color, grandparent color. Whenever a parent is red, our uncle color is important. Uncle color matters the story here. See now, if the uncle color is red, you have to do these two things. When uncle color is black, then you have to do these things. So 4A, 4B are very important, guys. 4A and 4B are very important. See this. Let me to clean this once. So we have to concentrate on 4A and 4B. This only I am increasing, see. 4A and 4B you take mainly. Whenever a parent is red, Whenever parent is red, check the color of parent sibling, that is uncle. If uncle color is red, then do something. If uncle color is black, do something. I'm underlining this here. If uncle color is red, do something. Uncle color is black, do something. I'll take this in two different cases. Currently, what is uncle color? What is uncle color is red. So red means I do 4A. 4A. Do 4A. In that 4A, two tasks are there. Change the color of parent and uncle to black. In this is the case, when uncle is red, immediately change the color of parent and uncle to black. Change the color of your recoloring. Your recoloring is one solution for balancing the red black trees. So what you're doing, guys? Recoloring. You do the, I am calling as a recolor this term. Like a rotation, this is one technique. Now, what should be the, what I have to change here? Immediately change parent and uncle to black. What is the parent? 35. Oh, sorry, uncle 35, parent 75. Change it to this. And first, second is change the color of grandparent to red if the grandparent is not root. Currently, what is the grandparent? 50. Grandparent is a root. Can I change the color to red? Grandparent is the, I have to change the grandparent to red. Can I do that? No, you should not do that when it is a root, because root always the black. So it will be in a black only. Make it black only. Now, any changes to 90, that done. I have done 4A this, 4A this. Then over. 90 remains the red only. Now you tell me, guys, is this fine? Is this fine? After recoloring, is this balanced or not? Means it is following the red black tree properties or not? Yes, it is following the red black tree properties. It is following the red black tree. Have you done any rotations? Have you done any rotations? No, we just recoloring has done the. So here, one other advantage of red black trees is we won't do so many rotations. In the case of AVL tree, in the case of AVL tree, in the case of AVL tree, okay, in the case of AVL tree, no, what is that? Because grandparent is not the root. Ah, yes, yes, correct, correct. Here is a mistake. Change the color of grandparent to red if if the grandparent is not red, not root, correct. This is gone. Yeah, you're right. So in the AVL tree, whenever it is becoming unbalanced, we do rotations. There are more rotations happens. AVL trees are more strict and more rotations happens every time whenever it is becoming unbalanced. Here, not so strict, so less rotations, and also we won't do all time rotations. Sometimes we need, if we need, we'll do rotations and solve the problem. Sometimes just because of recoloring. Recoloring means what to do, how to change a recoloring. Changing the uncle and the parent to black means you are changing that 1 to 0, 0 to 1. Small change. That is almost a big O of 1 only, right? Changing color is a big O of 1. Easy task than doing a lot of rotations, right? So is this clear? Okay, I'll take another case now. How to do another case? Creating the case is the We need to take a parent is black. Okay, I'll do that. So take the second example. This is the one case. Second case I'm taking, guys. First I'm inserting 50. So root is a black. Okay, fine. Next. I will do 75 directly. I'm inserting 75. Up to this, is this fine, guys? Is this fine? Anyway, 50 will have a null node. I'm just, for your understanding, I'm representing null node here. Is this fine? Is this red black tree, guys? Up to this, it is a red black tree, right? Yes. Now 90 I'll go. Insert 90. Always when I insert a new node, that will be the red node. Yes, 90 I'm inserting that as a red node. Now, is this okay for you? Is this okay? Is this a valid red black tree? No, it is not a valid red black tree. Then what I have to do, guys? What I have to do? You see the rule number 4. If the parent is red, 90 is the current value. X is 90. X is 90, correct. Parent is 75, which is in red color. Parent is 75, which is in red color. Current node is in red color. X is 90, current node. Parent is this. And grandparent is 50, which is in black color. Now, uncle is null, right? Uncle is null, which is in black color. This information always you need. Now, what to do, guys? Here, you see parent is red. When parent is red, you do this. Check the parent's sibling, uncle. Uncle is red or black. Uncle is red, we see in the previous story. Now 4b. If uncle is black or a null node, this is either black or null node. Anywhere null node is a black. Both are same, right? Now, if a parent is, uncle is, that is parent's sibling, which is uncle is black, you do the rotations. So we are not doing rotations all the time. Only when uncle is black, we are doing rotations. Uncle is red, we are not doing rotations. So some rotations are reduced in the red black tree when you compare with A wild. So first do rotation, then do the recoloring. Both required. Do rotations, do recoloring. Now tell me, which rotation I have to do here? You can tell rotations are same as we discussed. We have 4 types of rotations. So LL rotation, RR rotation, LR rotation, RL rotation. Same 4 rotations as it is, there's no change. Now tell me, because I inserted 90, my red black tree becomes unbalanced because not following the properties. I'm checking the parent. Parent is red. When parent is red, I have to check the parent's sibling, uncle color. Uncle color red, only I have to recolor it. But uncle color is black, then I do rotation, then recolor. So which rotation I have to follow now, guys? Bikash is telling RR. Valmiki is telling RR. Yes, it is RR. Because right. Very good. Right means do the rotation. This is RR rotation. RR means which side we have to do rotation, guys? Left side. Do the left side means you do the rotation like this. Before doing the rotation, for your understanding, I am telling guys, you should know you should know X. You should know X, current node 90, parent 75. Its colors also you should know. Parent red, grandparent 50 is in a black. Grandparent 50 is in a black. You remember this. Okay. Now do the RR rotation. Easy for you. Easy for you. Tell me, after doing RR rotation, what's the change? What should be the root, guys? What should be the root? 3 nodes. I think 75 red. Keep as it is. Currently 75 red. Keep as a red only. Next, 75 left child is the 50 black. Okay. Then 75 right child is a 90, which is the red. As it is, you keep. The 50 black you can represent. Currently, I am not showing. So, is this okay now? Is this okay now? Is this valid now? Not valid. That's what your job also not done. You've done the rotations done. When an uncle is black, you've done the rotations. Next, you have to do recoloring also. You have to do recoloring also. When you're doing the recoloring, when you're doing recoloring, guys, here important is to do the recoloring. I have points here. And these are the points we got already. So I'll just 4 rotations. I'm trying to keep this in a single line to save the space. 6th point important for us now. 6th point is how to do recoloring. What is the recoloring strategy? Recoloring is different when you do LL-RR rotations. Recoloring is strategy is different when you do LR or RL rotations. Currently, what rotation you have done, guys? You have done the RR rotation. If you do RR rotation or LL rotation, single step rotation, then what to do? You do this. Simply you do this. Swap the color of parent and grandparent. Swap the color of parent and grandparent. So what is the parent here? What's the parent here, guys? Parent is, you should remember these values. You should remember these values before rotation. Before rotation. Before rotation. I'll write that again. 75. Here I am writing, guys. This is, you see, 75 is the parent, which is in red color. Next, 50 is the grandparent, which is in black color. Before rotation, these are you have, okay? And X is the 90, right? We don't want anyway X, but keep it, which is X 90, which is the X current node, which is in red color. These 3 values you have to maintain before you do the rotation. Means I've written here. Now do the recoloring. When you do recoloring, which is the rotation you've done? RR rotation. 6A. If you do RR rotation or LL rotation, what you do? Swap the color of parent and grandparent. So what is the grandparent here? Grandparent is 75. Swap the color. Swap the color to red and black. So P 75, what should I draw? 75 becomes black. And what about 50? 50, which is already in black. I have to change to 50 to red. 50 to red. And 90, any change? No, 90 remains the same. This is what we have done is recoloring is done. Rotation and recolor. Rotation and recolor. Is this clear, guys? And if you've done a LR rotation or RL rotation, a 2-step rotation, double rotation, in that case, you swap the color of current node and grandparent. This only change. In the case of LL, RR, change the parent, swap the parent and grandparent colors. In the case of LR or RL, you swap the color of current node X and grandparents. Is this clear, guys? I shown you both here. LR, RL I didn't show, but anyway, we'll do the rotations again. So in the case of, if the parent is red, what to do? If the parent is red, if parent is black, what to do? Parent is black, nothing to do. Cool. Parent is red, then check the color of uncle. If the uncle color is red, only do the coloring enough. Uncle color is red, only do the coloring, recoloring. Just as shown the first case. Uncle color is red, only recoloring enough, no rotations. If uncle color is black, second case I've taken, uncle color is black here, you do rotation and recoloring. When you do the rotation can be LL or RR, or it can be LR or RL. So if the rotation is LL or RL, In that case, you swap the color of parent and grandparent. If you do the rotation, LR rotation or RL rotation, then swap the current node and color of current node X and grandparent. Automatically, it becomes valid red black tree. So the points are clear, guys. This is the most important. If you know this, I think you can start writing the program anytime. Is this clear, guys? Any doubts on this? Okay. Next. We do the rotations. We'll understand rotations and recoloring a little bit more. Go to next page. So first I am taking is LL rotation. LL rotation. So in LL rotation, we need the keys first. Important are the keys. In L rotation, what are the keys I have to consider? Have you remembered the keys? Same will take 10, 20, 30 scenario. LL rotation I want means I think I have to go for 30, 20, 10. This only gives me the LL rotation. So I have this data 30, 20 and 10. So I am creating a binary search tree, and my binary search tree must be I am creating a red black tree, which is a self-balanced BST. First insert, guys. Insert first. First, what we have to insert? 30. Insert 30. So as of now, I don't have a tree. So first I am inserting 30. What is the color? 30 is the black. Okay. Because this is the root. So 30 black. Okay, done. Done. Next. 20. 20, where it will come? Left side. 20 will come the left side. And I know this is a new node I am inserting. It should be the red. 20 left side, I am making it as red. So as of now, any objection? I think as of now, this is a valid red black tree. Am I right? This is a valid red black tree. And here, for your easiness, I am taking null here. 30 null. Next, I am inserting 10. 10 should come again, the left of this. It should be the red again, because the new node always red. 10 here. So is this okay for you? When parent is red, what we have to do, guys? When parent is red, check the uncle color. Parent is red, you have to check the uncle color. What is the uncle color here? Parent is 20 and parent's sibling is null, which is the black. Okay, black or null. Null is anyway black. So what to do? So this is the case where I have uncle is black. When uncle is black, you have to do rotation plus recoloring, both, right? Rotation and recoloring. Okay, first do the rotation. First do the rotation. Which side I have to do? What is the rotation? Is it LL only, right? LL. LL means you move towards the right side. This anyway rotation, you know, right side you rotate. First do the rotation. This is LL rotation, so that you are moving right side. And before moving, important guys, before moving, you should know the LL rotation means what you have to swap. After swapping LL, what do you need? Recoloring. Recoloring, what you have to recolor? Parent and what you have to swap, guys? Parent and grandparent. So you hold the values of parent and grandparent. What is the parent? 20 is the parent, right? So here I'll write 20. Parent is 20, which is in red color. Next, grandparent is 30, which is in black color. Okay, this is the status currently. Keep these values. Now you do the rotation. When you do the rotation, what should be the root, guys? 20 becomes the root. 20 becomes the root. Then 10 will be the red as it is. 30 is there as a black. Okay. This is not okay. That's what they are not allowing only do rotations. This is whole process not done, right? Only rotation is done. We have to recolor because this is not ready. Then you do the recolor. Recoloring. Do that. Recoloring means currently parent is 20 red, right? Parent 20 red. Make this black. 20 to black. Done. Next. Next is your grandparent 30, which is a black. You have to make it red. So my 10 remains the, so no, not red this color. I need a red color. 10 is as it is. We're changing only 20, 30. Is this valid, guys? Yes, absolutely. This is valid. Okay. Next, second case I'll take. Let this to here. Second, I'll take LR rotation. We'll finish LR rotation. LR rotation, what are the keys required? Tell me. LR rotation, what are the keys required? 30. Next, I do insert left, means smaller, 20. Then I had to go right. No, 30. I think I need a 10, 20, right? 30, 10 and 20. Okay. So start with 30. 30 is the always the root black. Next, 10. 10 should go on the, it should be red, right? 10 should go on the left. Yes. Then uncle is null only, right? Uncle is null. Null is always a black. Then I am inserting 20, guys. 20 should come on the right side. So this is not acceptable. This is not acceptable because red is parent. Parent is red. When parent is red, you have to check the color of. So the first case we have seen, guys. See this. In this case, what is the uncle status? Uncle is black. Uncle is black. So here also you have to keep a null node always. You have to keep a null node always. Okay. So 20 is parent is, you write down this. Current is X. 20. X is 20, which is in red color. And then grandparent is 30, which is in black color. We need these two because we are doing LR rotation. In the case of LR rotation, what we have to swap? We have to swap the current with the grandparent. So currently grandparent 30 in black color and X is the current in the red color. So LR rotation means, as you know, it is a two-step rotation. First do the LR rotation. Rotation 1, this will go to left side. So you do like this. Do that. Your 30 root becomes the same, and this is null as it is. And when you swap this, 20 comes here. Sorry, red color I need. And see, remaining, I think same as the above, see? Same as above, 30 black, 20 red. So next, same I think. I don't have option to copy paste, otherwise you do this. Next I have to do, guys, right side. Next rotation is towards right. So here also you've done the right. So right means you do like this. Then you will get red 20 on the top red 10 here and black 30 here. So rotation is done, you have to recolor now. Do the recoloring. Recoloring case, when you do LR rotation, we have to swap the current node with the grandparent. Colors of current node X to currently red is there. You make that as a black. Okay, make that as a black. So 20 becomes a black. Grandparent is black. Make it red. And same 10 remains as this. So is this fully balanced and obeying the rules of red blacks. So we have done this with LR rotation and LR rotation. Similarly, we have two more, that is RR and RL. Do that. Next, go to next page. Third rotation we are seeing is RR rotation. So here the keys I am taking. RR rotation, what keys required, guys? RR. Tell me the keys we want to produce RR. Right. Guess the keys. Have you practiced or not? AVL trees. 30, 40, 50, but okay. We are taking three values, 10, 20, 30, right? I'll take as 10, 20, 30. Higher all, ascending order sorting. Yeah. Are done. Okay. Start with this. First, insert 10. 10 is my root, which is the black. Fine. Then insert 20, which is the red. Then insert 30, which is the red. So no objectable. It's not it is objectable, right? Same thing you are doing in AVL tree also. Remember it. But the approach in AVL tree, what you are doing in AVL tree, you are checking the height every time. When height is becoming 2, then you are doing the rotations. Here, what you are doing, when you are violating the red black tree properties, then doing the rotations. Okay, so this is not okay, and we have a black here, guys. Parent is red, so parent is red means check the uncle color. Uncle is black again here. Uncle is black means we do the rotation. Rotation is required in this, right? Rotation is required on this. Do the rotation. Which rotation I do? Left side, you do the rotation. RR. So do the left side like this. Before doing the rotation, very important point here, guys. What is this is RR rotation. RR rotation means what you have to swap? Tell me that. RR rotation means what you have to swap, guys? RR rotation means what you have to swap? You have to swap the grandparent and parent color, or uncle and parent color changing is that is in the case of when uncle is red, because you're telling uncle red. Now uncle is black. Do the rotation. After rotation, swap the colors. When you're swapping the color, if you do RR LL, then swap the color of parent and grandparent. And in the case of RL and LR, swap the color of current node with grandparent. So this is RR. You're doing RR. Swap the color of parent and grandparent. So to do that later, currently hold the values of parent. Parent is 20, which is currently in a red color. Next, grandparent is a 10, which is in a black color. Just for our understanding purpose, I am holding like this. Okay. Now, rotation, do the rotation. 20 is the red, guys. It comes the root. Then 30 will be the root only. Black 10 becomes the black here on this. Then recoloring is required, guys. Recolor, what to do? Swap the parent. Red is there, change the parent to black. Parent is 20, make it black. Wherever 20, make it black. Done. Next, grandparent 10 is the black, change to red. 10 I have to change to red. 10 change to red. And 30 remains as it is. So now this is valid case. Clear? One more, the last rotation. This is LR. See, always RR rotation is a part of LR rotation. So I think I have to do RL rotation, right? Yes, RL rotation I have to do. For RL rotation, keys. RL rotation 10, 30, 20. Yeah. 10, 30, and 20. Okay. Start the tree creation. First, I have a 10, inserting 10, which should be the black always. Good. Next, go to 30. 30 should come as a right first. It should be red, right first. Fine. And we have a uncle black here. Okay. Then 20 should come as a left, right, left, right, left. So red parent, not okay. When a parent is red, check the uncle. Uncle is black here. Uncle is black here. Uncle is black, do the rotation. This is RL rotation. So first do the first rotation is R1 is, before doing the rotation, this is RL rotation means what you have to swap, guys? Swap the X and grandparent. What is the X? X is 20, which is in red color, and a grandparent, GP, grandparent is 10, which is in black color. This we have to swap it later. Okay. First rotation I have to do towards the right. How right means this comes. So do that. 10 remains the same here. Uncle is the black only here. So it comes 20 and 30. See, this is same as above tree. Same as from this onwards, the same as that. So next you do the right side rotation. Do like this. This is the rotation 2. And you will get 20 here, 30 here, and black 10. Done. This is not, still not okay because recoloring is pending. Recoloring, repainting, something like that. Now what to do? X is the 20, change it to black. So 20 to black. 20 to black. Next 10 is a grandparent which is in black, change it to red. 10 to red. And 30 remains same. Now it is happy. All the rules are done. I think because of doing these 4 rotations, practice again. Recoloring. I hope the rotations, recoloring, all that, all the rules are clear, I think, right? This is the left side. Sorry, I done left side, but written sentence wrongly. It is clear about red black trees. All the rotations clear, rules clear, properties, rules, rotations, recoloring. This is what important. Okay. Now what we do is we will take one example. One sample data will take bigger. We'll try to generate the red black tree by following all that. Assume you know everything in the red black tree. I'm going to another page here. So my keys I am taking here are 10 minutes. I'll complete this. 10 minutes. I'll complete Pankaj. After finishing this, we'll take a break. Okay. Generate red black tree. My sample keys are, I'll take the keys as 5, 15, 2, 10, 12, and 20. These are my keys. You have to just follow that and generate. Okay. Start. So first take the 5. Take the 5, guys. So 5, as of now, I don't have any nodes empty. So 5 is my root. So it should be the black. Okay. Make the 5 as a black. First step done. 5 as a black, single node is valid. Next. Add insert a 15. Next insert 15 means what should be the color of 15? You answer it quickly. I'll ask you everything. Whatever you understand, please answer. What is the color of 15? Red. Which side? Left or right? Left or right? Right side. Wonderful. Red, right side. No problem. Next. Next. 2. 2, which color? Red color. And which side? 5's left. 5's. As of now, I think it is valid only. Still valid only, see? Still valid, right? As of now, we are fine with the rules of red, black tree. Next is the 10. I am going. 10. 10 should be the red. 10 should be the red. And where I have to do this? 10 should be the red. And I have to make this as 15's. 15's lesser than 15. So 15 left. Red is coming here. 10 is coming here. So this is a, now I have an objection. Because red child, red parent, red black tree won't accept the red child, red parent. Now what to do, guys? When a red parent is there, what to do? When red parent is there, check the color of uncle. If the uncle color is red, if uncle color is red or black here? So what are the conditions? I am just writing conditions for you here again one time. If uncle color is red, if uncle color is black. If red, what to do? Tell me. Uncle color is red, what to do, guys? If uncle color is black, what to do? What you remember? Tell me. If uncle color is red, what to do? I think just recoloring only, right? Just recoloring. Yeah, how to do recoloring? We'll study later. Just recoloring only. No rotations. Am I right? Remember, no rotations. No rotations if the uncle color is red. In uncle color is black, then do rotations plus recoloring. This is an important first strategy. This in the rules were written as a 4A and 4B. If uncle color is red, no rotations, only recoloring. If uncle color is black, then do rotations plus recoloring. Okay, right. So it is red now. How to do recoloring? How to do recoloring? We have to change the uncle and parent to black. How this? There are 2 rules here. For under this rule number 1, whenever uncle is red, then change the parent and uncle to not swap. It is because it is not a swap. Straight away change the uncle and parent and uncle to black. Change to black. So what I am doing here, this is a recoloring, simply recoloring. Why I am doing only recoloring? Uncle is black. So when uncle is red. When uncle is red, change the color of parent and uncle to black. No, don't use the term swap here. No swap here. Change the color of parent and uncle to black. So I have a parent 5, which is a black. Currently, parent is 15. Red changed to black. Uncle 2 changed to black. I just recolored. Now, is this okay for you? Is this a valid red black tree? Is this a valid red black tree? Yes, valid. Without rotations, we solved the problem. Okay, done. Next, 10 is done. Next, 12 add insert, guys. Where add insert? 12. Go to 12. 12 where it comes. 10's right. Okay, 10 because of a new node, it should be the red node and right of this. Yes, 12. Now check. Now check. Is this red parent? Red parent means not okay. Red parent means check the color of uncle. What's the color of uncle here? 12 is that. 12 is the current node X, right? This is X. Parent is 10. Parent's uncle. Parent uncle is black only. How can I say? Because 15 will have a null node right here indirectly. Null node. If parent uncle is null or a black, anyway null is black, any rule, null. So black. Black means what to do now? If uncle is black, do the rotation plus do the recoloring. If uncle is black, do the rotation and recoloring. So which rotation, guys? Which rotation here? Which rotation? LR, right? LR. See, 10 left side. Then this is 12 you insert on the right side. It is a LR rotation. Do the LR rotation. So before doing the LR rotation, what we discussed, we should hold the values of in LR rotation. You have to do two things. First, do the LR rotation. Number two is if the LR rotation, what I have to swap? What I have to swap, guys? Swap X and GP, grandparent, right? Swap the colors of X, current node and grandparent. Swap the colors of current node and grandparent. So you just hold the values. What's the current node X? So here X is the 12, which is in red color. Grandparent is, what's the grandparent of this? X. 12 grandparent, guys. 15. GP grandparent is 15, which is in black color. Okay, so we will use those data after some time. Hold there. So first do the rotations. First rotation I am doing LR rotation. In that first one, rotation one, in that LR left side you do. Left side means I think I do like this. Am I right? Yeah. Redraw after this diagram. 5 and 2 is the black. 15 remains the same. The null may be required for you, or whenever required you draw that. So do the rotation. So here the 12 comes and here the 10 comes. Done. Rotation 1 is over. Now do the right side like this. This is your rotation 2 R2, which is on the right side. So our root is 5 black and 2. This is not 20. This is 2. Then after doing the rotation, guys, 12 becomes a root, I think. 12 becomes a root, which is a red now. It's 10 is the red only. 15 is the black, which becomes child of 12. So done. Now rotation is over. After rotation, recoloring. Recoloring is recoloring. Do recoloring. Recoloring, what to do? Just to swap the colors of grandparent and current node. Grandparent, current node X is the 12, which is in red. Make it to black. So make it to black. Let me to draw this again. 5 and 2. So 12 is a red. I have to make it to black. Okay, done. Next. Grandparent 15 is a black. I have to make this to red. And 10 is it acceptable, guys? Yes. And indirectly, you see, indirectly also, you see height is reduced. What is the goal of red black trees? What is the goal of red black trees, guys? What is the goal of red black trees? Reducing the height, minimizing the height, whether it is done or not. See, so here is the 12. Whenever I insert here in this diagram, I insert a 12, then height is 1, 2, 3, 4, or 1, 2, 3 at least. Now because of that I balanced it. Now reduce to 3 only, right? Height is reduced or not? Whenever I insert 12, it is going for more height. I reduced it to 3 only. Height reduction only. Either you do with AVL tree or red black tree. Yes, both are same. Next we will go for one more element. 12 is done, adjusted. I have a one more 20 is the pending eyes. If you insert 20, then I think over. So 20, where 20 will go? 15's right shade. Wonderful. 15 right shade. 20 here. Yeah. Oh, now parent is red. Parent is red means not accepted. So when parent is red, check the parent's sibling, uncle color. Uncle is red. Uncle is red. What to do? Uncle is red, guys. What to do? Uncle is red means recolor. Recoloring. Yes. So immediately just no rotation, right? Only recolor solves our problem. Recolor. Okay. In this recoloring, it is very simple. First, let me to draw this as this, above as this 5 and 2. These two let me to keep. Remaining, I'll do that. See, when a uncle is red, what I will do? Change the color of uncle and parent to parent color. What I will do, guys? Parent and uncle to black. So 15, I have to make it as a black parent, and uncle, that is a 10, I have to make it as a black. I made it as a black. First step is change the color of parent and uncle to black. I done. Parent is 15, uncle is 10. Change it to black. Straight away change it to black. Done. Next, second point is change the grandparent color to red. Change the grandparent color to red if that grandparent is not the root. Currently, who is the grandparent? 12. So whether 12 is the root, 12 is not the root. 12 is not the root means I have to change the color of 12 to red. Change the color of 12 to red. Then your 20 anyway remains as a red only. Now you just make the connections, guys. Is this acceptable according to the red black tree rules? Yes. Okay, guys. Is this done? Now I'll just add extra values. Tell me, I'll insert a 14 here. Extra, I want to insert a 14. Where I'd insert a 14, tell me. Where I'd insert a 14, guys? 14. 15's left. And color should be red only, right? Now, any objection to you? Is this fine? Is this fine? Yes. It is a valid red black tree. Next, I'll go for a, for example, what else I have? 9 I want. I am inserting 9. Where I'd insert 9? 9 will be inserted as a red. 9 will be inserted as a red. Where I'd insert? 10's left. Okay, no problem. No problem. I'll go for 11 insertion. 11. 10's right. 11 is here. No problem. Next, I'll go for a 3. After 9, it is 11. This is 11, guys. 11. And this is, I'll go for a 3. 3 left of this. Right of this. Now, it may cause a problem, right? If I, no, it won't cause. What is that? 3 I have taken. Okay, 3 here. Then that's it. If I take a 1, for example, after 3 you make it as a 1. 1 means left of 2. Any problem because of this? No. So whatever I inserted here, if you see, guys, I inserted now freshly 14 inserted, 9 inserted, 11 inserted, 3 inserted, 1 inserted. 14, parent is black. 11, parent is black. 9, parent is black. 3, parent is black. 1, I inserted, parent is black. So whenever I insert this 1, 3, 9, 11, 14, the parent is black. When parent is black, what to do? Parent is black, what to do, guys? When parent is black, nothing to do. There's a point number 3. Point number 3, that is. That's what. Only when parent is red, you do the checks. Can we revise the rules again here? Come back. Rules. Root always the black, no problem. Next, every node you insert should be the red. Fine. Rule number 3, if the parent is black, nothing to do. Only if the parent is red, then only go for checking the uncle color. If uncle is red, only recoloring. If uncle is black or the null node, then you do the rotation plus recoloring. Rotations we are done very clearly. Again, I told here, recoloring we understand. When you're doing a recoloring after the rotation, recoloring, LL or RR, in that you swap the color of parent and grandparent. In the case of LR and RL, you swap the color of current node and grandparent. Right? If the uncle is black, then you're doing rotations and recoloring. If uncle is red, then you do change the color of parent and uncle to black straight away. Change the color of grandparent to red if the grandparent is not the root. If the grandparent is not the root. That's about red black trees story, guys. Is this clear? I think we understand fully about red black trees. What are red black trees? What are the properties? What are the rules when you're generating red black tree? We understand the rotations, recoloring. We're taking a sample data to generate the red black tree. That as this example we are done. Still, you can do more practice, guys. Do more practice. For example, if I insert 25, what happens? Tell me now. If I insert 25, guys, 25. On this screen, you are seeing that if I insert 25, 25 will go to right of 20. So 25 will go to right of 20. Then parent is red, correct? 25, parent is 20, which is red. When parent is red, your story starts. Parent is red. Then you apply the parent is red. Then you see the parent uncle. Parent uncle is red only. Red only it is. Then do the recoloring. That's it. Okay, guys. So like that, for a better practice, only you do more times practice. You take the pen and paper, you draw this, whatever I'm drawing, it takes time maybe. You have to spend a quality time to you draw this all in your papers. Then that will be registered in your mind for longer time. Okay, guys, that's about red black trees and end of the binary search trees. Okay, problems we'll discuss in the lead code. Binary search tree now, concept over. Then some problems of BST we discussed, and more problems on BST will be discussed with lead code sessions. Okay, guys, thank you.